You guys, it's 3 a.m. So my last video I did on McLaurin series, Power series, and McLaurin series. In this video, I thought it would be appropriate to do a video on Taylor series, which, like McLaurin series, is also a Power series. So McLaurin series and Taylor series are subcategories of Power series. They're both Power series. So all McLaurin series and all Taylor series are they're all Power series, but not all Power series are McLaurin series or Taylor series. So let me write out the general form for a Power series. We have the summation from k equaling 0 to infinity, and then we have our coefficient c sub k times x minus a raised to the power of k. So coefficient, the indice k is it's dependent on the index. It's dependent on the index of the summation and then raised to the power of k, which is also dependent on the index of the summation. And we talked last video about McLaurin series. I think this is how you spell it. And I'm not sure. I don't know if that L is supposed to be capitalized, but we're gonna roll with it. We're gonna roll with it regardless. So the McLaurin series, it has this general form. See, that's k equals 0, the summation from k equals 0 to infinity of c sub k, our coefficient, and then instead of being multiplied to a binomial where there's a subtraction of a, which is a um is where it's centered at. There's the McLaurin series, it's centered at 0 every time. So we just get rid of a altogether because you're subtracting by 0. So this is going to be x raised to the power of k. All right, and then this video will be about Taylor series. Yeah, let me just write out the general form. And then we'll get into the gossip. It's not gossip, it's just the mathematical facts, at least from what I understand. So the Taylor series is the summation from 0 to infinity of, let's see, f, the kth order derivative of f, right? So how do I articulate this? I don't think I've ever like said this out loud. I think I said this out loud once. This is the function f raised to the kth order. So the kth order derivative of a. I think that's how you say it. Over k factorial multiplied to x minus a raised to the power of k. K of course corresponding to the index as the factorial responds, or excuse me, corresponds to the index, and so does the order of the derivative. So the gossip is that it's not gossip, it's fact. A Taylor series is a power series that represents a function using the function's derivative values at a chosen center A. So A is given to us, it's no longer 0. Um, and it builds an infinite approximation for a function. Um, so let's work through a problem and hopefully it will be a little bit more clear the difference between a power series, a McLaurin series, and a Taylor series. I also made like another video, like I think like 2 days ago on Taylor series. I just never posted it because I have to edit it and like that's time I could be spending doing math. But let's go ahead and work through a problem for Taylor series. Imagine that we have a function f of x, and the function f of x is set to sine of x. This has a center point, and the center point is a, and it's set to 5 pi over 3. Let's say that we're prompted to find the first 3 non-zero terms of the Taylor series for the given function that's centered at a. Well, the Taylor series of the function f of x um, at the point A, which you could say x equals A, it's given by this theorem that I'll write out. So we got f of x equals f of A plus f prime of A times x minus A plus f prime of A over 2 factorial times x minus A raised to the second power. Well, we're going to to get started on finding the first three non-zero terms uh, for the Taylor series for this function here, we need to find the components for this formula. Oops, we need to find this. We need to find the components for this formula. The first being f of a. So f of a is sine of a, and sine of a is 5 pi over 3. Wow, that looks atrocious. Okay, wait, hold on. Hold on. I don't mean to be so particular. I just let's make sure we can read this, right? So, um, sine of 5 pi over 3 is um it's something it's not a special angle. Well, it is a special angle, but it's something that it's a value that corresponds to the unit circle. Now, over time, I've actually grown to really like the unit circle just because I it's very convenient. It's very convenient. So here's our unit circle, right? Let's clean this up a bit. Let me just put this over here, okay? Here it's 30 degrees. Here it's 45 degrees. Here it's 60 degrees. This isn't drawn to scale, but I probably shouldn't have to say that. This is 90 degrees right here. And then let's see, we got 120, 135, and then 150. Then over here it's gonna be, well, right here is 180, right? 180, and then we're gonna go to 210, 225, 240, and then right here, which is where we're interested in, this is gonna be 300 degrees, also known as 5 pi over 3 radians. So, um, all right, and then and that's not, it should be clear that's coming directly from the origin. So this here, this is 300 degrees, um, 5 pi over 3 radians, and um, and so there's an x and y value for this. The x value is 1/2. The y value is negative root 3 over 2. Okay, when we're dealing with the unit circle, sinusoidal sine of x is always going to be the y coordinate. And then likewise, cosine of x, also known as complementary, it's complementary, right? Up to sine of x. Well, this is going to be the x coordinate. So let's see. We can also just write 300 degrees here because this is what we're interested in. We're going to be dealing with these. So if we do sine of 5 times pi over 3, we're going to look at the y coordinate. We're going to look at the y coordinate here. So we have y and x. That means that sine of pi, excuse me, yeah, sine of 5 pi over 3 is going to be negative root 3 over 2. And then that will be our f of a. As for as for f prime of a, well, then there's a requirement to find um, f of x's derivative. If you take the derivative of sine, it's going to be cosine. The derivative of sine is cosine. Well, it's straightforward enough. That means that, oops, that means that f prime of x equals cosine of x, but we want f prime of a, which is, well, that's going to be cosine of a. But we are interested in specifically cosine of 5 pi over 3, which we have the value for 300 degrees on the unit circle. And cosine is the x coordinate. So now we're looking at 1/2. So this equals 1/2. Then we need to find the derivative of f prime of x. So the derivative of cosine is going to be, I think it's negative sine, right? I think it's negative sine. Negative sine of x. Let's go with that. I'm pretty sure it's negative sine of x. And that would mean that we want, well, that means that f double prime of x is going to be negative sine of x. Of course, we want um we want f double prime of a, right? We want f double prime of a, and well, that's the same thing as negative sine of a. And instead of writing a in there, we're just going to go ahead and put in our 5 times pi over 3. Now, we know that the y coordinate corresponds to sine of x on the unit circle. So we're going to be looking at negative root 3 over 2. But we already have a negative sign right here. So we're just going to go ahead and write out that root 3 over 2 because those negatives are going to actually cancel. Um, and so at this point, we got everything we need to put on for a formula up here. So this is going to be f of x, which is equal to sine of x, is going to be sine of x equals well, f of a, which we found to be negative root 3, no, negative root 3 over 2 plus f prime of a, and we've got f prime of a already, which is 1/2, right? 1/2. But then we have to do our multiply it by the binomial x minus a, but instead of a, we're just going to put a 5 pi over 3 inside of those parentheses there. And then we'll move on to plug in to our third term here. which, let's see, this is gonna be negative, oh no, no, it's not negative. Root 3 over 2 over 2 factorial times x minus 5 pi, right? So we're just plugging in for a. And then we're going to raise this to the degree 2. Then we can simplify this. And so this is going to become negative root 3 over 2 plus 1 half times x minus 5 pi over 3 plus, we're going to do some simplification here, 2 factorial. Let's just write this out here. 2 factorial. Wow, that looks, okay, there we go. 2 factorial equals 1 times 2, which equals 2. So we're just gonna have a 2 in the denominator. This is a complex fraction. So if we reciprocate, we're gonna have, in the numerator there, we'll have root 3 over 4, because it's gonna be 2 times 2, times x minus 5 pi over 3, raised to the second power. And that's going to be the first 3 terms, but we could continue onward. So now it's like, imagine that we want to write, this in summation notation. How could we do that? How could we write the power series using summation notation for the first 6 coefficients of the Taylor series? Well, we're going to have to find the first 6 coefficients of the Taylor series. And honestly, I kind of want to like squeeze this in right here. Let me see here. Can I write out a little formula here? Let's see. C sub k equals f for the kth derivative of um, a. So in this case, 5 pi over 3. Okay? And, well, this is going to be over k factorial. That's not very neat now, is it? Let's see. I have an idea. Yeah, let's try to line this up here. Okay, I mean, like, not my best work, but it'll do. Will it? Will it do? Oh no. Let's see. Yeah. Oh, maybe. Anyway, so that's our formula for that. At this point, let's just write out our derivatives like rapid fire for f of x. We're just gonna do f of x. We'll just write that out here. We'll just rewrite it for just why not? So f of x equals sine of x. Now, f prime of x, well, f prime of x equals cosine of x, because we're just taking the derivative of sine of x. Then we want double prime of x. F double prime of x, you take the derivative of cosine, that's going to be negative sine of x. And then if we're going to grab the f triple prime of x, that means we're going to take the derivative of negative sine of x. Now that's going to be negative cosine of x. And then if we take the fourth derivative of our function, if you take the fourth derivative of sine of x, well, it's going to be sine of x. And this pattern will continue for every 4 derivatives. They're cyclical. They have a cyclical nature. Now, we're gonna take. Let me see here. What's the fifth derivative? This is where I stop putting the primes in. And I know this looks exponential, but it's not exponential. This is the fifth derivative of our function sine of x. So that the fifth derivative, so the derivative of sine is cosine. So derivative of the fifth derivative of sine of x, or the derivative of sine of x, is just going to be cosine of x. Right? So let's see now. At this point, well, we know f of a. We got f of a right here. And then we have um, f prime of a right here, 1/2. Then f double prime, um, well, f double prime is right here, root 3 over 2. And then no, we didn't. So now we'll go ahead with the calculation of the third derivative. So we have to find f triple prime of 5 pi over 3, and that's going to equal negative cosine of x. No, it's not. No, it's not. Just kidding. Did I say negative cosine of x? I meant 5 pi of 3 over 3. 5 pi over 3. And let's see, negative cosine 5 pi over 3. 5 pi over 3 cosine x coordinate 1/2 negative sine negative 1/2. Negative sign, just to be clear. Negative 1/2. Um, all right, then we're gonna run for the fourth derivative. The fourth derivative, um, and then we're gonna in the parenthetical statement here, we'll put 5 pi over 3. Um, that's gonna be sine of, because we know the fourth derivative, right? Sine of, actually put it a little bit of a different notation here, but that's okay. A sine of 5 pi over 3, and so this is gonna be a negative 3 over, no, negative root 3 over 2. And I know this because sine y coordinate negative 3 over 2. Excuse me, negative root 3 over 2. My apologies, guys, my apologies. Um, this is going to be the fifth derivative of sine of x, but we're going to plug in, instead of x, 5 excuse me, 5 pi over 3. And then that's going to be, well, the fifth is going to be cosine of x. So cosine of x, but not cosine of x, because it's actually cosine of pi over 3. And then cosine x coordinate 1/2. Right? And so at this point, we want to find like our c sub k's. So we'll start at c sub 0. We'll do c sub 0 equals well, it equals f of a over 0 factorial. What is that? What why did I make a dash? Okay, there we go. 0 factorial, right? Um well, let's see here. F of a, we know that f of a equals negative root 3 over 2 over 0 factorial. 0 factorial is just going to be, we'll say 0 factorial equals 1. And so that means that this is just going to be negative root 3 over 2. Then we want our c sub 1. And our c sub 1, well, that's going to be f prime of a over 1 factorial. All right, well, that's just going to be, we know that f prime of a is negative, or excuse me, f prime of a is 1/2, just positive 1/2, no negative. I don't know why I said that, but it's f prime of a is 1/2. 1 factorial is going to be 1. So that means we have 1/2 over 1, also known as 1/2, right? Then we're going to go ahead with our c sub 2. C sub 2 is f double prime of a over 2 factorial. And, well, that's going to be root 3 over 2 over 2, complex fraction, reciprocate, and we could just do that in our heads because we're going to get 3 over 4. And then another way that we could write this, well, I don't want to be too confusing, but another way that we could write this, which might give us a little bit of a leg up on our analytical investigation for how we could write. I don't want to get ahead of ourselves. This might help us with pattern recognition and analyzation later on, which is what we're going to do when we do the next part of this. But let's see. We could do c sub 3, and that's going to be third derivative of a over 3 factorial. Of course, 3 factorial is just going to be 6 because, well, 3 factorial equals 3 times 2 times 1, oops, yeah, times 1 equals 6, right? 3 factorial 6, um, and, well, f triple prime of a, what did we find that to be? Let me see something here. This will help us from just kind of just having our callouts ready. So, um, the third derivative right here, negative 1/2, and then we're going to get this going for the fourth derivative right here, and the fifth derivative right here. So let's see, the third derivative is going to be negative 1/2. So we're going to have negative 1/2 over 6 because 3 factorial is 6, which is just going to be negative 1 over 12 after we reciprocate. Also known as negative 1/2 times 1 over 3 factorial. And, well, let's see here. Mm, yeah, let's see. 3 sub 4, well, it's going to be the fourth derivative, so f of 4 of a over 4 factorial, that's a 4. My humor is so broken. Like, if I see like a number drawn weird, like I'll just start laughing at it. 4 factorial. Let's see, 4 factorial. 4 factorial, it's well, that's gonna be 24, right? 4 factorial, let's see. Because 6 times 4 is 24. So 4 factorial, it's gonna be 24. But this this the fourth derivative is gonna be it's gonna be like negative root 3 over 2. Negative root 3 over 2. I'm trying to think about how we could reciprocate this. So 24 times two, it's over 2, so 24 times 2, it's going to be 48. 48. And then, wait. Oh, but it's going to be negative root 3. And we could also write this as negative root 3 over 2 times 1 over 4 factorial. 1 over 4 factorial. And then the last one, let's see. It's gonna be c sub 5. And this is the last one because we wanted the first 6, but we're starting at 0, so it is 6. Um, and so this is gonna be, let's see, uh, the fifth order derivative for f of a over 5 factorial. And then 5 factorial is going to be 120. And then for the derivative, for the fifth order derivative, that's going to be 1/2. So we have to do 120 times 2, which is going to be 240 in the denominator there. And then we're going to have 1 on top. But then we have to do, let's see, 1/2 uh, times 5 factorial if we want it from a different orientation. So now comes the point in time where we want to look at this information and we want to analyze it. We want to analyze it in such a way because we want to like have a general form to like represent our Taylor coefficients. So we want to look for patterns. Um, we basically want to analyze this and investigate this so we can generally represent the different order Taylor coefficients, namely the even order Taylor coefficients and the odd order Taylor coefficients. So when we look at the C sub k's, let's investigate like the even indices. So what's going on with our even indices? The even indices, they start at C sub 0. So we got C sub 0, C sub 2, C sub 4, and those will be our even indices. So we can write it, our Taylor coefficient, let's see, C sub 2 times k. And we could write it in a general form such that it will represent the even order of our Taylor coefficients. So looks like we start at negative root 3 over 2. Negative root 3 over 2. So we could write out negative root 3 over 2. And interesting. So we're analyzing the indices that are even. So C sub 0, negative root 3 over 2. C sub 2, well, we get positive root 3 over 4. Then C sub 4, we get negative root 3 over 48. The interesting thing here is that the signs alternate. So what does that mean for us? Well, whenever you see like an alternating signs, you're trying to write like summation, you can put this negative 1 here, negative 1 raised to the power of k. And here on the bottom of this c sub k here, there's a factorial. And we can write the even indices for the factorial. We could write 2k factorial. But what about for the odd indices? What about for the odd indices? For the odd indices, we could put c sub 2 times k plus 1. So for the odd indices, we got c sub 2 times k plus 1. That's going to always be our odd indices. So our odd indices go from, let's see, we got c sub 1, 1/2, um, c sub 3, negative 1/12, c sub 4, no, c sub 5. It's going to be 1 over 240, or 1 over 2 times 1 over 5 factorial. So we start at 1/2. So we could put 1/2 times the rational expression, because they do alternate, -1 raised to the power of k over, this is no longer 2k factorial, right? 2k factorial down here, right here in the subscript. 2k plus 1 factorial is what's going to be in the denominator. We should probably throw some parentheses on that and indicate that it's a factorial. So now the final thing to do here would be to put this into summation notation. Um, and we cannot just put this with one, we can't just put this with one sigma. We need to use two separate sigmas because separate, there's either, there's two different types of Taylor coefficients. There's the ones that with the even indices, and then there's the ones with the odd indices. The even indices need to have their own separate sigma symbol. Odd indices need to have their own separate sigma symbol, and only then can we put it into sigma notation. So let us begin by writing out the summation for the even indices, which is going to be from k equals 0 to infinity. And we're just going to write what we have for c sub 2 times k, which is going to be well, it's going to be negative root 3 over 2 times the rational expression -1 raised to the power of k over 2k factorial. But we're not done there. We can't stop there because we if we look at what the Taylor series is, we have this is our c sub k right here, what we just came up with, but then we need to multiply it to this binomial x minus a raised to the power of k. Um, so we're gonna multiply it to the binomial x minus a, but we know what a is, so we're not gonna put a. The series is centered at 5 pi over 3, so it's gonna be x minus 5 pi over 3. Okay, but then we're going to raise it to the power of 2k, right? Then for our second summation, which is going to be this is going to be the representative of the odd indices, right? We're going to have let's see, we're going from k equals 0 to infinity. For the odd indices, um, c sub 2 times k plus 1. Well, we're just going to plug this in here. 1 over 2 times the rational expression -1 raised to the power of k over 2 times k plus 1 factorial, right? Um, then we're going to do x minus 5 pi over 3. And likewise, so, we raised this over here to the power of 2 times k. This is a 2k plus 1 because it's for the odd indices, so we're going to follow suit with that. 2 times k plus 1. This here is going to be our answer of how we can put this into summation notation. This is this is the power series in summation notation. So yeah, pretty cool though. Pretty cool though. It's a little bit of unit circle action going on, taking some derivatives, come up with a way to put this into summation notation. I just love this kind of stuff. I just think it's cool. Um, but yeah, that's how you do that. Now, earlier in the video, I had mentioned that 2 days preceding the recording of that video, I had made a video on Taylor series. It was more of a general video on Taylor series, and I try to attempt to explain what's going on. I'm just going to clip it on the tail end of this video that was just played because they both have to do with Taylor series. Enjoy! What are Taylor series, Taylor polynomials? Like, what even is that? Imagine that like we have a function. And I'm gonna try to do my best to explain this. I'm still learning this as I go. I think sometimes explaining things when I'm learning really helps me cement information. But hey, if I've made a mistake, please let me know in the comments. By all means, please. I would appreciate that. Um, and so yeah, so like imagine we have a function f of x equals e raised to the power of x, and like we want we want to use like a simpler function. Like, can we use a simpler function that can approximate this, like to in like a way that's like close to zero? Like, can we use a simpler function? Can we use a simpler function to approximate? And let's approximate it near x equals zero. So we're gonna do this near x equals zero. Imagine we use a constant function, and I'm just gonna go ahead and is our question here. Oh, okay. All right, you guys are playing Tetris. Oh man. Okay. Yeah, so we're gonna attempt to try to find a simpler function to approximate e raised to the power of x near zero, okay? And the first way that we could do this, I think, is to use a constant function. And a constant function like could be like if you think about it graphically, like it's just gonna be like a straight line, right? So a constant function on a graph would be like y equals a, right? Maybe y equals 1, y equals 2. It's just gonna be a straight line across the x and y axis. But let's do y equals a so that y of 0 equals f of 0, which means that instead of e of x, we're going to have e of 0, and then that's going to equal 1, because anything raised to the power of 0 is 1. So then, so then that's going to mean that y of 0 equals 1, and then a of 0, a, a, not a of 0, a is going to equal 1. Let's just imagine like the function, right? So we have c of x. Let's say c of x for constant. C of x equals 1. This is just the way I learned it. So c of x equals 1, and then we're gonna imagine the function f of x equaling e raised to the power of x, like on our graph here, x and y, our old friends, and so we're gonna go 1 and 2, and then we're gonna go 1 and 2 in the opposite direction. And e raised to the power of x, the exponential, so it's gonna look um like uh, let's see here. 1, if this is 1 here, and up here it's like 1, 2, 2, so it's gonna cross over like about 1 right here. Maybe I should use a different color or something. So it's gonna cross over about 1. And so let's just draw what this is gonna look like. It's gonna look like this. Nope, not like that. No. Kinda. Okay, the exponential. And let's see, like up here, we'll say that this is the arrow going up. We'll say that this is gonna be a 1e. All right, x equals 1, y equals e. All right, this right here is 2, so then I guess this here would be 3. Um, so like e is like 2.7, so maybe up here would be 3. And so we're going down, and then because we have a equals 1, right? So then we're going back this way, and right here we could put a point, call this -1 and 1 over e So that's an e. Um, and then well, and then we have our constant function. Then we have our constant function, and we'll put this in a like a nice purple color. And and so the constant, like we're doing c of x equals 1, so that's gonna be like right here. And I'm gonna just put it as like a dotted line so we can still read that, hopefully, right? And so that will be c of x equals 1. And and you remember we're trying to get like an approximation for this function here. So, you know, like this isn't great. This is like I think like this line, it's like maybe like from like here, here to like here, it's okay, right? But like it's not like and even then it's like not that good. Like this is just not really what we're looking for. Like, we're trying to do an approximation. We're trying to get it to look we're trying to use a simpler function to describe e raised to the power of x. And like this is a line and like yeah, it's okay at this point kind of, but like not really. It's not that great. So that's our first attempt at that. And we're doing a constant function attempt, right? So you can call this attempt 1. Well, now we're gonna do like a second attempt because we're not really satisfied with that. All right. Um, let's like do a linear attempt. And so a linear attempt, that's gonna be like y. This is gonna be y equals mx plus b. Y equals, but instead of m for the slope, let's do a for the slope since we were rolling with that before, right? So y equals ax plus b. All right, now we're switching it up a bit. Um, but that's just our y equals mx plus b. But instead of an m to show the slope, we're showing an a with a slope. So the a is the slope, and we're gonna do this so that oh well, so we'll do this. Well, let me just we'll do this so that we have y of 0 equals f of 0. Okay, and then y prime of 0, its derivative is going to equal y prime of 0. And so like if we have f of 0, if we have f of 0, then that's going to be e raised to the power of 0, and that's going to equal 1. And if we have f prime of 0, its derivative, that's just going to be, well, oh, I'm sorry. What would we want with f prime of 0? F prime of x. If we take f prime of x, of the derivative of, maybe we could write this out real quickly. Let's see here. The derivative of e raised to the power of x is, well, that's just going to be e raised to the power of x. All right. And that's what's nice about that. So, um, so like, yeah, so, you know what I mean? And, uh, and so this here, it's going to be e raised to the power of x. And um, then e raised to the power of x. So if we take the derivative of that, that would mean that now we want to deal with the f prime of 0. Well, that's going to equal, that's a 0. Pardon me. That's a 0. Equals e raised to the power of 0, which is 1. And then, well, that's going to mean that we got y of 0 equals 1, and then y prime of 0 equals 1, where where I'll say Or maybe let me just back up here. What's even going on? What's even going what's even going on? Okay, well, so when we look at y prime of 0 equaling f prime of 0, we can see here that the slope stays the same. The slope the slope is the same. Okay? And then and we want y of 0. Like we want this. We're like we want this. Okay? Like we're like, yeah, like we want that. All right? And so and so so we're looking at this here, and and we have y y equals no yes y equals a times x plus b. then then we have y prime of x equals a. This is the derivative. A is the derivative, but we want to do another shot at drawing this. We need another shot at trying to like graph this, because we want to see what happens as we graph it. And so plugging these in, right? Plugging these in, let's see. Uh, and I'll just try to do this over here. We've got a of 0 plus b equals 1. All right? A equals 1. Now, we have a equals 1 and we have b equals 1. All right? And and so like we can we can graph this. We can graph this here. So if we put like L of x, L for linearization, or excuse me, L for linear function, then L of x equals x plus 1. And L equals x plus 1 because if we look at our what's this called? Well, that's called slope intercept form. Anyway, so if we look at slope intercept form right here, um, y equals ax plus b, and we plug everything in, you know, we're gonna get we're gonna plug in. Well, we found that a equals 1. Okay, a equals 1, so we plug in a, it's 1 times x. 1 times x is x. Okay, then we know that b is equal to 1. And so what that means is that we're going to have x plus 1. So we're going to graph L of x equals x plus 1. And note that the linearization of f of x at x equals 0, that's just going to be the tangent line. The tangent line is the slope at a point. It means that the curve's instantaneous direction at that exact point. Um, so yeah, a tangent line, it's a straight line that just touches a curve at one point and it has the same slope as that curve at that point, right? So we're gonna go ahead and we're gonna try to attempt to graph this here. Let's roll with this blue color because we did this for the last function of for the last depiction of e raised to the power of x. So this is -1. We'll have a point right here. Okay. Oh yeah. Wait. Okay. Well, and then let's just count up. 1, 2, 3. Like right here, I'm gonna start really seeing that. Like so, probably cross over like right about here. Which ideally this would branch out more than like that. Yeah, let's go with that. just misses it altogether. Just just entirely misses the dot that I put. Okay, hold on, wait. All right, there we go. Well, okay. That's not a straight shot, but it's, you know. And so this is gonna be f of x equals e raised to the power of x. All right, and um, then we're gonna have like a, well, we did in purple here c of x, and we could bring back c of x in this season, in this episode. We'll bring back c of x, right? Um, and so that will be right here. And then now we're gonna do um the linearization. Now we're gonna do the linearization. And so we have x plus 1. So 1, right? That's gonna intercept right here on the y-axis. And then the slope is 1. So we're gonna go up 1, side 1. And it's gonna be like right here. And then down here. Just pretend that this is a straight line. I mean, I know it's not. No, it's not. But let's just pretend. And then this is going to be L of x equals x plus 1. All right, this is closer. This is closer to like an approximation. Remember, we're trying to approximate this function here in blue. And like when we look at this, it's not great. Um Certainly it's like better like over here. It gets closer to it. So this is the linear attempt. This is the linear attempt. It's certainly better, but but we can make the approximation hug the function. We can make it approximate the function closer. However, to do this, we need to up the complexity. We need to up the ante of the equation, if you will. So we did 1 right here, okay? This is 2 right here. And then let's do another attempt. Let's try to attempt to use a simpler equation than e raised to the power of x to approximate um to approximate its value, what its line, to make it look. I'm just gonna say it. We want a function that's not e raised to the power of x, that looks exactly like e raised to the power of x graphically. That's a simpler function, but it can approximate its value. It can approximate the value of e raised to the power of x. Okay, and so now we're going to do an attempt um, with a quadratic equation, quadratic a quadratic attempt. And what we can see is happening here is like, as we're trying to do this, the functions are getting more complex, but that's okay, because because then we can approximate it a lot um approximate it a lot closer to the value. So q for quadratic, q of x, and then the quadratic tends to look like a times x raised to the power of 2 plus b times x plus c, right? Um, and so that's our quadratic there. And and so like when it comes to the quadratic, well, we have a quadratic q of x equals a times x squared plus b times x plus c. Okay, where q of 0 equals f of 0 and then q prime of 0, that equals f prime of 0, and then q double prime of 0, double prime of 0, its second derivative, the second derivative is going to equal the second derivative q double prime of 0. Now, what's really going on here? Well, we got q of x equals a times x raised to the second power plus b times x raised to the second, excuse me, raised to the first power. A times x raised to the second power plus b times x plus c. And then, well, we want to take this derivative. We want to take the derivative. To take the derivative with respect to x, if we take the derivative of this quadratic here, let's see. Let's try to do this in our heads. Q prime of x. The derivative here, a times x squared. Well, I think that's a power rule. So then that a will come out, we'll do a times 2x, right? A times 2x. And then factor out that b, we'll take the derivative of x, which is just 1, and then with the derivative of c, well, I think that's just going to go away. So the derivative is going to be 2 times a x plus b is the first derivative. So then that's the derivative with respect to x, and then we're going to take the second derivative. We're going to take the second derivative, q double prime of x, and then so then 2 times a 2 times a times x plus b. Mm. The derivative of that is this is just going to be 2 times a. And now what we must do is, so maybe I should leave a bit of room. We're going to work this way. So then we have q of 0. Q of 0 equals f of 0. And q of 0 equals f of 0, and this is going to equal 1. Then um, then we'll plug in for 0, so that would mean a times 0 raised to the second power plus b times 0 plus c, I think, equals 1. And then that's just going to give us, c equals 1. And then for the first derivative, q prime of 0 equals f prime of 0. Hmm. This equals 1, and then I think it's like 2 times a times 0 plus b equals 1, which that means that b equals 1. And then we'll sort of just follow suit here with the second derivative, q double prime of 0 equals f double prime of 0, right? F double prime of 0, and then this is going to be 1. And then we could plug in because we found the derivative. We're just going to plug it in here. Um, this is 2a 2a equals 1. And then could divide both sides by 2, and then a equals 1/2. I think. I hope. And then let's go ahead and we'll just write this out then. So we've effectively got our coefficients here. We've effectively got our coefficients here. And this is going to be q of x equals 1 over 2 x squared plus x plus 1. Yeah, I think. And then, so this is the linear attempt. This is the constant attempt. Where are we here? A equals 1. And then we got our cubic attempt. Excuse me, our quadratic attempt. I don't know why I said cubic, because we're gonna do cubic next. Spoiler alert, we're gonna do cubic next. Um, grab this orange here. Look, I'm gonna just graph this. I'm just gonna graph this on this one here, that we already have, just for just because. And so if we were to graph this, and I'm just gonna use my TI-84. I'm gonna use my TI-84 because I regret to inform you that I don't know how to picture this graphically just in my head yet. Maybe one day. Maybe one day, but okay. All right. Yes. So I see what's going on here. Let me try to draw this. Okay. So basically, this is what the graph of the quadratic is going to look like. We're going to have um well, it's going to be like a parabola kind of thing like this, right? But it's going to like start coming down here, and like the vertex is going to hit like right about here, and then it'll cross over at 1, interestingly enough, and it will sort of just shoot up. All right, we just shoot up. And now, as you can see, this is a little bit more of an approximation on these intervals here, right? A little bit of a closer approximation. So I'll say that this is. We're not really interested in what happens here, but just I'll just kind of draw it there because it is a parabola. And we'll just call this q of x. Then there will be an arrow because it's going up. And there should be an arrow here too. All right, so the approximation is getting like closer and closer to f of x equals e raised to the power of x. But we can do even better because we could do a cubic. We could do a cubic. So this will be attempt 4. This will be attempt 4, and this will be the cubic. This will be the cubic episode. This will be the cubic attempt. Well, let's just write out like our standard like cubic form. So let's say like cu of x for cubic. Um, well, the cubic will look like this. A times x raised to the third plus b times x raised to the second plus c times x plus d. And this is like, and so here we'll say that kind of do what we did here before. Cu of x where Cu, oh no, wait, hold on, I don't have to write my u's like that. I mean, I could, but let's just do Cu of 0 equals f of 0, and that's going to equal 1. And Cu of 0, no, wait, hold on. Should be the derivative. Cu prime of 0 equals f prime of 0 equals 1. Cu double prime of 0 equals f of double prime of 0 equals 1. Cu triple prime of 0 equals f triple prime of 0 equals 1. And let's just sort of place some boundaries around that. Braces. And like let's just jump right in. Let's just jump right in because C Cu of 0. I'm just gonna go back to writing my U's like that, dude. I'm so used to writing my U's like that, just in math, that I'm just gonna roll with it. It's muscle memory, isn't it? Cu of 0. So now we're just gonna plug in 0 everywhere where there's an x. A times 0 raised to the third power plus b times 0 raised to the second, plus, and it's descending, so um, c times 0 raised to the first plus d, that's just going to equal 1. Then we'll do the derivative of that, cu prime of 0, which we know equals 1, and we're going to have, well, we're going to have to take the derivative. Oh, yes, we're going to have to take the derivative. What's the derivative of this? Let's see. I'm going to try to do this in my head. So I don't know if this is going to be right, you guys. So a times x raised to the third power, 3 is going to come out front, so it's going to be 3a x raised to the second. So 3 times a, and that x is, we're going to replace it with a 0. We're going to raise that to the second power. Not that it really matters because it's a 0, but we're going to do that. And we're going to add what to the, we're going to take the derivative of b times x raised to the second power, and that's going to be 2bx. So 2b, and then the x is going to become a 0. And then we're going to take the derivative of c times x, and we're just going to strip it of that x, and so that's going to become plus c, and then the derivative of d is going to be 0, and then this is going to equal 1. And what does that tell us? Well, that tells us that c equals 1. Now we're going to take, we're going to do c double prime of 0, so we're going to take the derivative of that, and so let's see, what do we have for the derivative of this here? We had 3a times x raised to the second. So that 2 is going to come out front when it's going to act with the 3 in such a way where it's going to turn into a 6. So we're going to have 6, 6 times a times 0, right? sorry, I'm just trying to think because what's going on with that 2b though? Is it 2b? 2b, well, it's going to equal 1. And then we can divide both sides, and that's going to mean that b, we're going to divide both sides by 2. Um, and then, so that would mean b equals 1/2, and then we're going to do that cu triple prime. Cu triple prime. And cu triple prime of 0, and this is going to equal 1. I know I didn't do it up here, but I should have. But we're just going to keep going. Um, but note that there should be a 1 here and then a colon, uh, for the sake of consistency, but I'm just going to keep going with this because I'm trying to do this in one shot. Alright, so now what? So, what's the derivative of 6 times a times x plus 2b? Like, wait, what? Hold on. I'm like tripping myself up. Um, 6a, which is, this means that 6a equals 1. Oh, I should say with respect to x. Because, yeah, the derivative of 6 times a times x plus 2b, derivative with respect to x. And that's just going to become, this is, so, and then if I divide both sides by 6, well, this is going to be a equals 1 over 6. And then let me just graph this really quickly. It's going to cross over the x-axis like, say like right here. And then it's going to kind of do like a little bit of a swivel where that's like, well, it's like right here, right? And it's going to be like this. And it's going to cross over at that 1 before it goes down like that. And so as you can see, the approximation for this, well, I just realized something. I didn't even write it out. Okay, wait, hold on. Yeah, no, hold on. Cu of x equals 1 over 6 because that's our coefficient here. Um, times x raised to the third, right? Plus our other coefficient, which is b. Plus, and I'm just plugging this in for this here, right? We found a, we found b, we found c, we found d, and I'm literally just plugging this in. So 1 over 6 times x raised to the third power plus 1/2 times x raised to the second power plus x plus 1. All right, and those are just our coefficients. And that's this right here is what the graph of that's going to look like. And hopefully that can help you guys understand. I saw this thing on Reddit, not Reddit, on Wikipedia that that showed me uh what really like a what's going on with the Taylor series. So I'll see if I can find that one. Let me see here. This is a Wikipedia article on Taylor series, and this is what I was telling you guys about earlier. But it's just the depiction of approximations while equations are getting more and more complex, right? They're raising the order, the degree that they're raising it, and then it's approximating closer and closer and closer to the function value. And that's exactly what we just did here. If you look at this graphically, and then I went on Desmos and graphed it for us to look at and sort of evaluate because, well, my graph, let's just say it's not the best, you know. And I have Desmos right here. And fun fact, in Greek, Desmos means bond. Anyway, so here's the constant function, right, in blue. So the function that we're trying to approximate is in red, right? That's e raised to the power of x. Here's the function, um, here's the constant function, right? C of x equals 1, right? Then we did, I think it was the second attempt was the linear, right? This is the linear attempt. This is the linear attempt in green. All right, and remember, we're still trying to approximate in red, okay? And then we did our quadratic here in purple, right? That's parabola. And as you can see, it's starting to approximate it right along this, like right here. It's getting closer and closer and closer to the red, to the function, right? And then I couldn't call this cu of x, so I just call it s of x. And that's our cubic. And as you can see, guys, look how close that gets. Look at how close that approximation gets, you know? Like we like that. So that's what I was trying to draw and show you guys. You know, in comparison to Desmos, it's not the greatest, but that's what we just did. All right. Um, moving on. Moving on. F of x equals ln of 1 minus x centered at x equals 0, which I think means that this is a Maclaurin series, Maclaurin polynomial, Maclaurin, centered at x equals 0 for n equals 0, 1, 2, 3, or say, and 3. That indicates that's the last one now. Um, okay, all right. So we want to find the nth order Taylor polynomial for the function f of x equals the natural logarithm of 1 minus x centered at x equals 0. And we want to do this for n equals 0, 1, 2, and 3. Well, um, first thing we have to do here, first thing we have to do is we have to take the derivative of f of x. We have to take the derivative of f of x. And to take the derivative of f of x, we have to use the chain rule. And the chain rule, well, it says that if we have a composite function, which we do have a composite function, and we have a composite function, y equals f of g of x, then then let's see, d over dx equals f of prime of g of x, I think it goes like this, and then you have to multiply by the derivative of the inside, which in this case is just g of x. Wow, that looks let's go ahead and touch that up a bit. Okay. Um so we got the derivative of the outer function times the derivative of the inner function. And so here the outer function is f of u, okay? And then that means that the outer function is f of u, which is the natural logarithm of whatever's on the inside, right? U. And then the the derivative of f of u, since it's a requirement that we take the derivative of f of u, we're going to need to take the derivative of the natural logarithm, and the derivative of the natural logarithm is just going to be, uh, hold on, I'm getting ahead of myself here. The derivative of the natural logarithm is just going to be 1 over u. And so then the inner function here is going to be u, right? And then the u is going to be 1 minus x, because that's what's on the inside right over here. And then what? We want to take the derivative of u. How do we take the derivative of u? Well, the derivative of 1 is going to be 0, and the derivative of negative x is just going to be negative 1. So the answer is negative 1. And then now we have all the components that we need to actually apply the chain rule in the first place. So upon applying the chain rule, I think let's just be specific here. The derivative of the natural logarithm of nope, 1 minus x. 1 minus x. Well, let's see, this is going to be like 1 over 1 minus x, right? 'Cause 1 over u, and then we can plug in for u, 1 minus x, times the derivative of u, the derivative of u, negative 1. Well, that's going to be um, negative 1 over 1 minus x. And so then what that means is that um, f prime of x, well, that equals negative 1 over 1 minus x. But then, since we're going to take the second derivative of this, it's probably a good idea to put it in this form here where we have a negative exponent, just because then we can run with a power rule when it comes to taking the second derivative and we're good to go. So now we want to find what is um what is f double prime of x? Like what even is that, right? And so uh to find that we're gonna have to take the derivative of the second to find the second derivative, we're gonna have to take the derivative of the first derivative. And so this is gonna be I'm just gonna stick this in the brackets here. 1 minus x raised to the power of negative 1, and and um and this is gonna be, no, I was wrong. I thought that I was like my brain was like, let's do the power rule, but my brain was wrong because I think actually we're gonna have to do the chain rule. I think we are gonna have to do the chain rule again, because it is a function. Because look, guys, there's a function inside of another function, so it's the power. We can't do the power rule because we have a function on the inside and a function on the outside. So, no, I'm wrong. The outside function is the power of negative 1, and then the inside function is the 1 minus x. A little bit trippy. Um, but 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 that's okay. That's okay because you can think about it as like, oh, it's inside the parentheses, right? So that would make the f of u, that's what we will do the power rule, is negative u raised to the power of negative 1, and then the inside function, well, that's going to be whatever. U equals 1 minus x, and then mm, and then we're gonna do the chain rule. And so so then we need to find the derivative of f of u. So f prime of u. Um, well, I think we can apply the power rule here actually. So there's some power rule action going on here, such that we'll just write it out here. It's good for the, I think it's good for the soul. Um, n x negative n in the exponential place. And so then that can get applied f prime of u, which is gonna be, the negative will come out front. I think it's u to the power of negative 2, I think. No, it's not. Is it? No, because that negative 1 is gonna come out front and it's gonna cancel, right? It's gonna cancel. So it's actually gonna be u to the negative second power is gonna be the derivative here. And so then that would mean that we still got to do the inside function still. So we'll have to take the derivative of, oh, this isn't, okay, so that's just going to be the derivative of 1, which is 0, and then the derivative of negative x, which is negative 1, so the answer is negative 1. So that means that the derivative of u is just negative 1. All right. And so, um, well, now we can actually go ahead with the application of the chain rule. So, so, I gotta retrace my steps. Negative u became, okay. So, okay, but u, okay, so it's gonna be 1 minus x raised to the negative second power times negative 1, which is gonna be, I'm gonna bring that downstairs. 1 minus x squared negative, because there's a negative 1, and then it's gonna be like that. That looks awfully close to the, okay, let's just do like that. Um, well, so that would mean that the second derivative here, so, uh, what did I put the first derivative right here, right? Let's underline that. So the second derivative here, f double prime of x equals negative 1 over 1 minus x squared, which can also be written as um like d brought up to the second, d times x brought up to the second to indicate that this is the second derivative. This could be written like this: 1 minus x equals negative 1 over 1 minus x, right? Or, oh yeah, squared. Yeah, to get rid of that negative exponent. Or if we want, negative 1 minus x raised to the negative second power. Okay, but we now we must find the third derivative, right? Like so go ahead and underline that. And so what's f triple prime? What's f triple prime? Um, well, since f double prime is over here somewhere, right here, we've written it out like this, which will make it a little bit easier. Negative 1 minus x raised to the negative second power. And so we're gonna have to find d over dx, negative 1 minus x raised to the negative second power. And we're gonna have to take the derivative of this, but we're gonna do this using the chain rule again. Okay, so we'll have to identify like what's the outside function and what's the inside function. Well, the outside function is sort of the same thing as before, where we have the negative 2 on the outside, the negative symbol on the outside. So we'll be able to set f of u equal to, let's see, I think f of u goes to negative u brought up to the negative second power, like that. And then we have to take the derivative of that, right? So f prime of u equals, oh no, I'm gonna need more room for that, but I think it's gonna be 2u raised to the negative third power, but we're not gonna do that over here. I think it goes like this. I'm not sure though. Let me just see here. Think about this for a second. U equals 2u raised to the third, negative third, right? And then I want to do u raised to the third in the denominator with a 2 on top, I think. Yes. And then the inside function, well, the inside function is going to be 1 minus x. And then, oh yeah, I said that we were doing the chain rule, right? Did I mention that we were doing the chain rule? This is the chain rule. 2, so okay, wait, 2, so we did 2, we got 2 over u raised to the third, and then we know that the inside function is 1 minus x. So I'm going to set u equal to 1 minus x. Find the derivative for 2, no, u, excuse me, u prime, which is going to be 0 minus -1. So that's going to be -1, I think. And then um, to apply the chain rule, then we do 2 over 1 minus x raised to the third power times -1 equals I think it's like uh -2 over 1 minus x uh raised to the third power. And so what that means is that f prime 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 of x is going to equal -2 over 1 minus x raised to the third power. All right. And what we had just done there is that we found the first, no, we found, yeah, we found the and first, second, and third derivatives for this. The second part of this question says that we want to graph the Taylor polynomials in the original function on the same set of axes, right? But I think we already found like what all of the derivatives that we requested to find are. Um, and so just to be neat, I'm gonna say like we got f prime of x, because we already have f of x right up here. There's no need to rewrite that, is there? I mean, we're reading these, but only because they're scattered throughout. F prime of x equals, I just want to get our bearings straight, minus f of f prime of x equals -1 minus x raised to the negative first. And then f double prime of x equals uh negative negative 1 minus x raised to the negative second. And then f triple prime of x, well, that's going to equal -2 times 1 minus x raised to the negative third, did we say? I think. And so now what we have to do is we have to find those values. We have to find those values right here. These values need to be found at x equals 0, because it's centered at x equals 0. Mm, and so let's just see here, because f prime of 0, right, for the original function up here, f prime of x, f prime of 0 equals, well, let's do ln of ln of 0. No, I'm just kidding. That's undefined, for just in case you didn't know. Undefined, anything equal to 0 or less than 0 is undefined for the natural log. It's just, I don't know. I'm just making a dumb joke. Anyway, f of f of 0 equals the natural logarithm of 1 minus 0, which is the natural logarithm of 1. The natural logarithm of 1 is 0. And then f prime of 0, right? F prime of 0, we're just gonna plug in for the f prime of 0, for where the x is for f prime of x. And so that's just gonna be well, here this is the same thing as as negative 1 over 1 minus x. So I could say negative 1 over 1 minus, instead of x, but 0. Well, the answer to this is going to be negative 1. All right, and then we could do f double prime of 0. Well, that's going to be, if we wanted to interpret this as a fraction, a 1 on the denominator, 1 minus, wow, that was not letting me draw a line for a second. 1 minus 0 raised to the second power equals, I think, negative 1. And then so then we're going to go with the f at triple prime and f triple prime of 0 at that, and that's going to be negative, and I'm just going to throw that 2 on top, 1 minus 0 raised to the third power, right? And then upon evaluation, this is going to be negative 2. So now that we've got that sorted, I'm just going to grab a swig of water really quickly. All right. Well, we have to do p of 0, or excuse me, p sub 0 of x. P sub 0 of x equals f of 0. Okay? And and well, let me see. And then f of 0 equals 0. F of 0 equals 0. So that means that p sub 0 of x equals 0. And then this is the 0 right here. This is the 0th Taylor polynomial. It's the 0th it's the 0th Taylor polynomial. Okay? And and I think at this point it might be appropriate to write out the formula. Let's do it right here. So this is how the formula goes. P sub 1 of x equals f of a plus f prime of a times x minus a. And this is gonna help us find the linear approximation at a, right? This is what we need to find the linear approximating polynomial centered at a, but in this case it's 0. Um, and then when it comes to P2, because this is we're gonna blow through this in like a second. So it starts to get a little bit more complex, right? Because for P sub 2 of x, it's gonna go like this. F of a, which of course in our case is 0, plus f prime of a times x minus a plus, that's a plus sign, plus f double prime of a over 2 x minus a squared. And then that's gonna be our other formula for the p sub 2. Do I really? Okay. All right, let's go. Come on. That's crazy. Wait, something just like feels wrong about this. Oh yeah, factorial. That's a factorial. Just note that's a factorial. Honestly, I'm just gonna leave it. This actually kind of looks cool. I would put it in blue, but like, doesn't that kind of look cool? Like, isn't that a little bit of a vibe? Okay, wait. That actually kind of looks cool. All right, wait. So I'm gonna leave it like that. Not just because I don't want to switch back, but basically, let's just keep the ball rolling. P sub 1 of x equals f of 0 plus, and we're just plugging it in this formula here because a is set to 0. Um, f prime of 0 times x minus 0. Well, that's going to turn into p sub 1 of x equals 0 plus negative 1 x minus 0, and that's going to equal p sub 1 of x equals negative x, right? Negative x, yes. All right. So now we need to plug in this formula here. Um, and so that's gonna go p sub 2 of x equals f of a, which is f of 0, plus f prime of a, which is f prime of 0, which is negative 1, right? I just want to be sure. Negative 1 times x minus a, which is going to be in our case x minus 0. Negative, uh, this is going to be, so plus, because f double prime of a is right here. So it is going to be negative. We could put it in the, yeah, let's leave it in the numerator, I would say. Um, or I could just bring it out front. F prime of, f double prime of a, f double prime of a. I'm going to bring this out front. So here's what I mean by that. A factorial of 2 is just 2, right? So we have negative 1 half, and then f double prime of a, f double prime of 0 is negative 1. So negative 1, that's, I don't know why I said that, bring that out front. That should be right there. There's nothing being brought up front. Sorry, you guys. Negative 1 half, and then finally we're gonna do this x minus a raised to the second. Well, instead of x minus a, we're gonna have x minus 0. It's still going to be raised to the second per the formula or the theorem. And also, and then if we simplify this, p so 2 of x, that's going to equal, well, f of 0 is 0 plus negative x minus 0, negative x minus negative 1 half of, no, yeah, wait, negative x minus 1 half um times x raised to the second power. Mm, I'm like pretty sure. And then so that's gonna be p sub 2, I think. This is the master formula. P sub n of x equals f of a plus f prime of a times, and you might notice this is looking a lot like our formula for p sub 2, but this is a formula that's applicable to any involving derivatives to the degree for any number n. So f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a raised to the second power plus anything in between all the way up to n factorial. And I'm aware of that, that's blinking there, and I'll have to move this over in a second. But this is the f, and then this n represents the primes, like factorials. Like if there was like a 3 where that n is, that would be the third derivative. If there was an 8 right where that n is, that would be the eighth derivative of the function. I'm just putting an n there for a placeholder. Wait, hold on, I'm running out of room. Oh, I have an idea. These formulas, we're done. All right, we don't we've moved on to this formula, which is this is again this is directly applicable to any derivative up to the nth degree, so it covers those guys. Um, and again, I should have just written this to begin with, but better late than never, I suppose. So here we go. So this is p sub n of x equals f of a plus f prime of a times x minus a quantity plus f double prime of a over 2 factorial times x minus a quantity squared plus anything in between all the way up to some number n. Okay? And so let's go ahead and let's apply this to our p. So we did p sub 2. So we're going to just jump right in. We're going to do p sub 3 now. So yeah, let's do p sub 3 equals p sub 3 of x, and this is going to be um f prime, no, not, there's no prime, f of 0 plus f of prime, or excuse me, f prime of 0 times x minus 0 plus uh f, this is going to be double prime of 0, 1, 2, 0 over 2 factorial, which is just going to be 2, um x minus 0 times x minus 0 squared plus 3 factorial, no, excuse me, the denominator is going to be 3 factorial plus f triple prime of 0 over 3 factorial times x minus 0 raised to the third power. Okay, let's do some simplification here. That means that p sub 3 of x is going to that's going to be equal to 0 minus 1 times x minus 0 minus, um, well, f double prime of 0 was identified to be -1, so it is going to be a minus 2 factorial, so it's going to be 1 over 2 factorial, which is just 2. Um, and then times uh, x minus a which is going to be x minus 0 squared plus, um, gosh, triple prime, uh, -2 in the numerator over, 6. I think 3 factorial, which is 6, because, and this, here's why. 3 factorial equals 1 times 2 times 3, multiplying everything up 1, 2, 3 up to 3, which is 6. Fun fact, factorials increase faster than exponents. I'm pretty sure they do increase faster than exponents, excuse me. Exponents. Um, they increase really, really fast. X minus 0. X minus 0 raised to the third power. Um, yeah. Yeah, so now I'm like running out of room here. Okay. I have an idea. Can I shrink this and just like put this right here for simplification purposes? Okay, but then write the real answer down here. Um, P sub 3 of x is gonna equal, well, this is all gonna be, so we're gonna, this is gonna be negative x minus 1/2 x squared minus 1/3 times x cubed. And that's gonna be our answer. That's gonna be our answer right there.